and reasoning about Boltzmann brains. And I thought I'd put up a picture from the top of Mount Temple in the Canadian Rockies, and there's Marine Lake at the bottom. This is the Valley of the 10 Peaks. It used to be on the $10 bill. Anyway, so if you have a chance to come to Canada and come to Banff National Park, there's lots of great beauty there. And if you have a long enough time to do a really long hike, you can hike up to the top of this Mount Temple where I'm viewing and where my, let's see, does my pointer work? Where my car is down there, right down there. Okay, so I'm going to, the talk I want to talk about has some speculative, it raises what I regard as important issues that we don't yet know in physics. And so I mainly want to emphasize what we don't know and what I believe should be done in the future. That is, what problems should be solved. I mean, I don't know how to solve them. And I'll have, some speculations about, well, some limitations on some things, and then some speculations of how to maybe get partial progress to this. But it's more raising problems than giving solutions. Although, it's showing some ways in which we might hope that there could be solutions. Okay, so in my mind, a complete theory of the universe would not only give the complete set of dynamical laws, what's been misleadingly called a theory of everything, but also the quantum state of the universe. And this is a main new part I would emphasize, the so far unknown rules for extracting the probabilities of observations from the quantum state. Well, you may say that's not by Born rule, but let me go on to say that that's not completely adequate. So I'll propose a basic framework for these rules, that the measure for each observation is the expectation value in the quantum state of the universe of a corresponding positive quantum operator for each possible observation. And I'll just name these an awareness operator. Now, this is a framework. It's not a theory because I don't know what the operators are. I don't have a theory for what the operators are. It's a framework, I guess, somewhat analogous to the way that quantum theory, you could say, is a framework until you propose what the Hamiltonian is or what the Lagrangian or the action or whatever. Just the principles of quantum theory is a framework, but not a complete theory. Well, similarly, what I'm talking about is a framework, but it's not a well-developed theory in that because it doesn't deal with these operators. Okay, you also need to say what operations are. And I'm going to make this somewhat radical proposal that they're fundamentally sentient experiences, or sometimes I call them conscious perceptions, each being the entirety of a conscious awareness, all at once consciously aware of it once. Now, if you don't like that, I mean, a lot of people say, this is getting off into things beyond physics, or others will say this would be things we just don't know. And I agree, we don't know the connection between consciousness and physics at all well. So if you want to think of a toy model, maybe you could say, well, an observation is the data in some computer. I mean, say the archive, say all the bits, the zeros and ones that represent all the information in the archive. You could think of that as a toy model, but I don't believe the archive is really conscious. So I tend to think that consciousness is something fundamental, and therefore, if I say that observations are fundamentally conscious perceptions, then it seems like that's something that at least I have some ideas to what that is, and well, to distinguish. Anyway, that's going to be in the back of my mind, that observations are fundamentally conscious perceptions. And I shall explain, for a large universe with indistinguishable copies of observers, the quantum awareness operators cannot be projection operators, as one might have assumed from Born's rule. Okay, so now I'm arguing that bare quantum theory is not testable. Bare quantum theory describes the universe in terms of quantum states, operators, expectation values, wave functions, amplitudes, path integrals, etc., but does not by itself connect these to observations. So the bare quantum theory is not directly testable. But to make comparison with observation, Max Born suggested that the wave function gives probabilities. Later it was proposed that the probabilities are given by the absolute squares of amplitudes, and these can be taken to be expectation values of projection operators. So in this, I should have said talk, I'll take the mathematization of Born's rule to be the idea that the probabilities of observations are given by the expectation values of projection operators. So now I like to use Bayesian analysis for trying to estimate the probabilities of different theories. So let's consider a theories T sub I. I'll, for simplicity, assume that there's a discrete countable set of theories, so you can have an index I that denote which one. And that for each possible observation, O sub k, and again, for simplicity, I'll assume they're discrete, although it could be they're continuous, but things are a little simpler if you imagine there's a discrete set. Okay, so that gives the probability of that observation, P of O, then vertical line T sub I. So this is the probability of the observation given the theory. If the theory is correct, what probability does it give to the observation? So now if we assign prior probabilities to the theories that are prior to any observation, and as far as I know, these prior probabilities, they're unavoidably subjective. But we do tend in science to take Occam's razor that we face simpler theories. So we generally want to have higher prior probabilities for simpler theories, though of course just saying that doesn't determine what these probabilities are. So this is something subjective as far as I can see, and I don't see how to avoid that. Okay, if you have that prior probability and then you use an observation O sub k to test the theory, it might be a complicated observation. I mean, it might have a lot of data within the observation to test the theory. then that's the probability of the observation given the theory, and it's what statisticians call the likelihood. It's slightly confusing because the likelihood is not the probability of the theory, it's really the probability of the observation given the theory. And then Bayes' theorem, we can calculate the posterior probability of the theory. In other words, given the observation, what's the probability of the theory? It's then the probability of the prior probability of the theory times the probability of the observation given the theory. That would be so that'd be the joint probability of the theory and the observation divided by the sum of this over all theories for which one assigns positive prior probability. So that's what you'd really like to get the probabilities for theories, and so you have to go through this procedure in Bayes analysis to do that. And of course, we'd like to find a theory in which this posterior probability is as high as possible by choosing a simple theory so we can get high prior probability that gives a good statistical fit to one's observations, O sub k, so high likelihood. We'd like to have both high probability, high prior probability, and high likelihood. Okay, now suppose if...
Can I ask a question?
Oh, yeah. Yes.
Hi. Sorry to know. So, but our theories generally we aim for the theories to be exact fits rather than the best probability, the highest, most likely fit, right? I mean, observations have uncertainties, but kind of our predictions kind of exactly match.
Yeah. So, I mean, of course, in some sense here, I'm doing this highly hypothetical thing that you have a complete theory for the whole universe. Mm-hmm. And so this complete theory, in some sense, should be able to predict something. Well, it's going to predict a whole distribution of different possible observations with different probabilities, but it should be able to predict, you know, if you observe something that's got uncertain data and your observations have this uncertainty, I'm imagining that the theory itself, the complete theory, could in principle predict what these variances are, what the fluctuations are.
I see.
So in other words, it should predict. Well, I guess take the example of tossing a fair coin 1,000 times. Well, the highest probability is 500 heads, but we know that we also have the theory that if each coin is independent, that you get a binomial distribution, and so you can get the probability of getting some number different from 500. So it's true, you're not getting a precise measurement of the mean if you toss it 1,000 times, because it might be, 500 plus or minus 30 something. But I'm saying the theory, if you had a complete theory, it should be able to predict the probabilities of all these of all the possible observations.
Okay.
But this is admittedly, I mean, I'm talking about a future theory. We don't have any such theory. A complete theory of the universe that predicts the probabilities of all possible observations. Okay, now in my mind, complete theory should completely specify all properties of that universe. And so you might think that it has no room for probabilities between 0 and 1. It just makes definite predictions. So you might say, well, certain observations do occur and certain don't. So then you would get that all likelihoods would be either 0 or 1. If the observation exists in this theory, you'd have 1. If it doesn't exist, you'd have 0. But trouble with that is then this posterior probability for the theories given the observation, it'd just be proportional to the prior probability of the theories that give that say that this observation have unit probability. So it would throw out some theories, but it would allow any theory that predicted this observation to exist. The probability would just purely be the prior probability. So there wouldn't be any. It would be very weak experimental evidence. It would only rule out some theories that don't have the observation at all, but it wouldn't be able to really test it. So even though I'm a theorist, I do think observations are very important in science, and I think observations should play a bigger role in science. And so we would like to have a way of getting a range of likelihoods between 0 and 1, well, possibly including the endpoints. Maybe I should have put greater than or equal to. But now, if the theories can give normalizable measures for the observations, then the normalized measures can't be interpreted to be likelihoods that can vary from 0 to 1. So in some sense, I'm proposing the thing that maybe the complete theory really is deterministic, but it still proposes measures for different observations. And then if you normalize the measures to add up to 1, then these can be interpreted as if they were probabilities. And in particular, if the probability of the observation given the theory, these likelihoods can vary between 0 and 1. All right, now give me an example. Suppose in a classical theory, the measures could be functionals of the phase space trajectory. You have a trajectory through the phase space. And one example could be the times that the system spins in different regions of the phase space. So if you imagine that, well, just to make it finite, that there's some finite extent of the time in the classical theory, then you could take the fraction of the time that it's in each region in phase space as the measure for it being in that phase space. And then you could, if you say your observation depends on where you are in the phase space, then the probability of each observation would be how long does the trajectory, the fraction of the total time that the trajectory spins in that region. So in a quantum theory, the measures could be certain functionals of the quantum state or maps from the quantum state to non-negative numbers. And should be normalizable. Now, another argument against likelihoods all 0 or 1 are that if a specific theory, T sub I, leads to the definite existence of more than one observation, O sub k, you might be tempted to say that this probability of the observation is 1 for all of these observations, giving unit likelihood for any theory predicting the definite existence of a particular actual observation. But this would mean that you could construct a theory of maximum likelihood, no matter what the observation turns out to be, by just having the theory predict that all possible observations definitely exist. So, if you say my theory predicts all observations exist, no matter what you observe, it's predicted by this theory, then, but that seems to be too cheap. It supposedly explains everything, but it actually explains nothing. It doesn't really explain why do we see the order in our universe, because if you say there's also exists highly disordered observations, this way of looking at it would say, oh, well, all we need is for it to predict that there are some observations, or there's some that match what we have, and who cares about all the rest of them. But that's sort of an objection that some people raise against multiverse theories. They say, well, it really is just predicting everything, and so it really predicts nothing. And I would agree for that type of multiverse theory. If you're predicting all observations occur with equal probability. So anyway, this idea of assigning unit probability for all observations that occur, I don't think helps in for making predictions. So I'm proposing the normalization principle, or maybe you could say meta theory, that each theory gives normalized probabilities for the different possible observations that it predicts. So for each theory, the sum of the probabilities over all the observations is unity. So that's why I propose you're not allowed to say that all observations have unit probability. You want the probabilities to add up for that. And okay, so we have this trade-off between prior probabilities and likelihoods. There's the prior probabilities for the theories. Those are sort of the intrinsic plausibilities, even without any observations. Of course, that's a little hard to imagine because, of course, for us to...
Can I ask something more related to the end of the last slide?
Yes.
So this very last, summing for a given theory, if you sum over all observables, possible observations,
right,
sum to unity. So suppose the theory was quantum mechanics,
right,
quantum theory, but you had a state which is the plus state, 0 plus 1, okay,
right,
and you took one observation which is the Z basis, which will have half probability, and then you also have the X basis measurement, which is like another okay, which can have a 1 probability. So maybe the observations okay are wouldn't be like different basis observations would not be the different okays, right? Is that...
Well, it would be. I mean, in this case, if you let's take this simple example. You have this spin a half system, and you have the first observer measures whether it's up or down in one basis. So there's two possible results for that observation. And then maybe he or somebody else makes a second observation, and there's two possibilities for that. And so in that case, I'd say that there's four observations. There's there's four possible observations. There's the first observation of up, a first observation down. There's a second observation of up, second down. And so then the theory should predict the problem. So if these are all the observations that could exist in the universe, and well, I guess it depends what this state is. I mean, if the spin was up and you measured it, whether it's in the X direction, up or down, then that'd be a probably. And then if you did that for the second measurement in the Y direction, then all four of these observations would have a probability of a fourth.
Okay. So you're taking it as two successive observations then yeah.
Yeah. So a sequence, those would be different, different observations, right? Okay, so the prior probabilities are these intrinsic plausibilities, and then these conditional probabilities for observations, or the quote likelihoods of the theories, and then the posterior probabilities are proportional to the product, and you have to normalize that by the dividing by the sum of that. So prior probabilities are subjective, usually higher for simpler theories. And the highest probability might be for the theory, let me call it T sub 1. And this is a theory that nothing concrete or contingent exists. It only maybe pure logical things like mathematics. Say if once you've defined things, 1 + 1 = 2, that could be true even if there's no actual universe or nothing. So let's suppose that's the only thing that exists, has this Platonic existence. There's no concrete existence. But then observations are concrete. I mean, they're not logically necessary to exist. I mean, you could have the world could be a blank with nothing contingent. But in this theory, that's a very simple theory. So you might assign it a high prior probability. Maybe I'd assign it a half, but then the probability of observation given this theory would just be 0. So then when you took the product, the prior would be high, maybe a half, but this probably 0. So that observation, the fact that we can observe something, that something exists, something concrete exists. Now, next simplest theory I can think of is T2. It might be the theory that all observations exist equally. But surely that there's an infinite number of possible observations. And so if you normalize it, you'd have to say it's 1 divided by the number of, which is infinity. So again, that would give you 0 for the likelihood in a theory in which you say all observations exist equally. This is a way in which I would say that we have strong evidence against what's philosophers sometimes call modal realism, that they assume anything logically possible actually exists. Well, of course, that's not quite strong enough to rule it out. But if I say not only everything logically possible exists, but each possible observation exists with each equal measure, then if there's an infinite number, then each one has 0 normalized measure. So you'll lead to 0 posterior probability. Okay, so that's sort of maximize trying to get things with high prior probability. At the other extreme, there'd be the maximum likelihood theory, giving unit probability for one's observation. Maybe one particular observation you make, you're going to test your theory. You could imagine a theory that just predicts that theory, only that theory exists. No other observations exist. But this seems to me to require a very complex theory. I mean, how could I have my present observation and yet there's no other observations? None of you really exist in the sense of making or being conscious beings making observations. And not only that, it's even stronger than solipsism, because it would say even my memories, the awareness of the memory would be part of the observation. But what I remembered, I would not have had any actual observations in the past. There would be memories of things that I never experienced in the past. I only experience now the memory of it. Anyway, I think this would be a very complicated theory. So of course, I don't know the details of such a theory, but I think this would be so complex, you'd extremely tiny prior probability. And so that would also give a low posterior. So I think there's this trade-off between prior probabilities and likelihoods, that is between intrinsic plausibility and fit to observations. Okay, now this goes into, there's the measure problem in cosmology, and that's how to obtain probabilities of observations from the quantum state of the universe. And it's particularly a problem when eternal inflation leads to a universe of unbounded size, so that there are infinitely many realizations or occurrences of observations in each of the many different kinds or types, making the ratios ambiguous. You get infinity divided by infinity, which tend to be ambiguous. And there's also a danger in cosmology of domination by Boltzmann brains, which are observers produced by thermal and or vacuum fluctuations. Now, this measure problem seems to be somewhat related, at least, to the measurement problem of quantum theory, how to relate quantum reality to our observations that appear to be much more classical. Which you might say is, how do you get high probabilities that the observations seem to be fairly classical, even if the world has huge quantum uncertainties? Well, as I mentioned before, an approach I shall take is to assume that observations are fundamentally conscious perceptions or sentient experiences. I use those two phrases synonymously. And each perception being all that one is consciously aware of at once, all that you're aware of at once. Now, for these probability of observations, I shall take an Everettian view. At least it's Everettian in the sense that I don't believe in the collapse of the wave function. So I'll assume that the wave function never collapses. So in the Heisenberg picture, there's just a single fixed quantum state of the universe. And it could even be a multiverse. It could be different amplitude, different components of this quantum state that have different coupling constants and so on and so on. Now, instead of some definite many worlds, in the Everett picture, there's different branches of the wave function, but then how do you define the branching? So rather than talk about how you might divide up the wave function different parts, the many worlds, I'm proposing there instead many different actually existing observations, many different sentient experiences. There's ones that each of you is having right now and that I'm having. There's ones that we've had in the past and ones that we'll presumably have in the future, and one's way off and maybe in other sentient beings on Earth, certainly, and then off in other places in the universe. And there may be also ones in what you might call different branches of the Everett view, although, as I say, I'm not, nothing of mine depends on making some particular choices of the basis for the quantum states to define branches. Anyway, but I'm assuming there are many of these and they have positive measure. Each one has a positive measure, let's say mu, because ma for measure, mu sub k, and that would be the measure of this observation, which is in some sense how much the observations occur. But the measure is not determined just by the contents. So a more painful toothache doesn't mean it has more measure, but I'm just proposing that there's some fundamental thing of this measure for the observation. Now, for simplicity, as I said, I'll assume there's a countable discrete set of observations and that the total measure is normalized to unity for each possible complete theory that gives normalized measurable for all possible observations. And then in a Bayesian analysis, I'll interpret the normalized measures, mu, of the observation for that theory that each gives to the probability given the theory, this thing, which for each observation is the likelihood of the theory. So this is a slightly tricky thing. I'm saying that even though it may be a deterministic theory, it may precisely determine what all these measures are. To test the theory, I'm going to act as if the measures, when normalized, are probabilities. They would be. I mean, if you imagine that there were, I mean, I'm not saying that there is a choice, because I'm saying all these observations really occur. But if you made a random choice of the observation, and by random you made a random choice with the probability given by the measure, then the probability that this random choice would choose a particular observation, that would be an actual probability. But that's bringing up this mythical idea of some choice of one out of this big set of observations. Okay, then I have a particular hypothesis about these measures that I've called sensible quantum mechanics, or in one paper for laymen, I call it mindless sensationalism. So the map from the quantum state to the measures could be nonlinear, but in sensible quantum mechanics, I assume it's linear. And I also, kind of as a joke, called it mindless sensationalism, because it proposes what is fundamentally is not minds, but conscious perceptions, which crudely might be called sensations, although I'm stretching it a bit, because the conscious include more than of what one's consciously aware of, for example, memories, and what's usually called sensation. So it's a little bit, but anyway, I just try to get a sensational title for the paper. Okay, so the measure for the observation mu, then it would be given by the expectation value of this operator in the quantum state. So sigma is the quantum state that gives expectation values to operators, or I could write it the expectation value, put the angular bracket around this operator. So it's the expectation value, A of k, and that could ultimately be written as the awareness operator for that observation. So this sigma is the quantum state of the universe, and I'm in the interpretation that a quantum state is a positive linear functional of quantum operators, and A sub k is a non-negative awareness operator corresponding to the observation or sentient experience. The quantum state sigma, it could be a pure state, it could be a mixed state given by a density matrix, or it could be a C-star algebra state. This is very, very general for which, well, in some sense, how big the state space is. And so the quantum state and the awareness operators, along with this linear relationship above, that the measure is given by the expectation value. And also you need to have a complete description of each observation. They're all to be given by this theory. So it's a very complete theory that we don't have at present. I mean, we don't know what the quantum state of the universe is. We don't know what these awareness operators are. And we certainly, we don't humanly have a complete description of all possible observations. So this is very much hypothetical in the future, but I'm saying this is what, I'm assuming maybe would be a complete theory of the world. Now, let me talk a bit about the Born rule and how it really doesn't work in a large universe. So traditional quantum theory uses Born's rule with the probability of observation OK being the expectation value of an operator that's a projection operator. So that means the product of two of them is 0 if they're different, and it's the same projection operator if j and k are the same. So no sum over k in here, just for a given j and k. So in that case, the probability of the observation is the expectation value of this projection operator corresponding to the observation. So Born's rule works when one knows where the observer is within the quantum state. For example, in the quantum state of a single laboratory of the universe, so that one has definite orthonormal projection operators. However, Born's rule does not work in a universe large enough that there may be identical copies of the observer at different locations, since then the observer does not know uniquely the location or what the projection operators are. So let me give an example. Suppose there are two identical copies of the observer at location B and C that can each make the observation O1 and O2, which does not reveal a location. So maybe there's a spin that's one place, maybe it's pointing one way, another place the other way, and you can't. The observer can't tell where he is, and he could make an observation of spin up or spin down, but that doesn't tell him where he is. So Born rule would be the probabilities. If you knew you were at B, the probability to get result 1 at B would be, in Born rule, the expectation value of that projection operator, and the result for the other observation at B would be that. That would be if the observer knew we're at location B, with the projection operators being this. And similarly, you get probabilities PC sub 1 for the observation 1 at the other location, if the observation knew it were at that. However, if the observant is not certain to be either B and C, and let's say, without loss of generality, that one of them is less than the other one, at one place it's more probable to get result 1 at the other place, then if you're uncertain, you should have some probability between there, because there's some uncertainty as whether you're at B or C. But there's no state independent projection operator that gives an expectation value with this property for all possible quantum states. So no matter what projection operator you pick, it's not going to give a number between that for all possible quantum states. So no matter what the orthonormal projection operators are, there's an open set of states that give expectation values that are not positively weighted means of the observational probabilities at the two locations. So the Born rule fails in cosmology if you have a big enough universe that you can have different observations. Maybe to give an example, let's just consider a simple case where there's two quantum states. There's a quantum state 1, 2 that represents the observation 1 in the region B and the observation 2 in the region C. And then there's the 2, 1 that represents the observation 2 in the region B and 1 in region C. So then the probability of getting result 1 in region B is the same as getting 2 in region C, because that's from this part. This part state has result 1 in there. And so the Born's rule would give that as the square of absolute square of that amplitude, and the probability of the other one would be the square of that amplitude. But now for Born's rule to give the possibility of both observational probabilities being non-zero in this two-dimensional quantum state, these projection operators must be of rank 1, because if they were rank 2, they would just be the unit operator in there, and then you just get unit probability for everything. And of course, it can't be rank 0, you won't get anything out. So it has to be rank 1. So in this case, it's just the bra and the ket from one state, and this is for some orthogonal state. But now the idea is, once these state independent projection operators are fixed, then if the quantum state were psi sub 1, the expectation values of the two projection operators are P1 is 1 and P2 is 0. So these expectation values are 0 and 1. They're extreme. They're not positively weighted means of these for any choice of this state. No matter what the state is, no matter what projection operators you use, then there is a state in which it's not a positively weighted mean. So no matter what the orthonormal projection operators are, there is at least one quantum state, and actually an open set of states that give expectation values that are not positively weighted means of the observational probabilities at the two locations. So I'm saying Born's rule fails if you can have more than one observer that can't tell where he is.
Don, if I may ask a question.
Right.
So in this example, it's a very interesting example. So now the question is whether B and C, the states which you have defined, is it the purity of the state? Is it really a good assumption? Because as long as B and C are both in the same causal patch, how could they, can I treat them as a pure states?
Well, I mean, this, of course, is a toy example where I just have a universe with two states. But I'm saying that this same thing would happen. I mean, even if I had more states and so on, or even if they're mixed states, I think you still run into into this problem. So the toy example is just to show how it works in the simplest sort of possible example I could.
You are saying even if I take it entangled state, your conclusion would remain be the same.
Yeah, well, and this, well, this state, of course, is entangled because the you have the two possibilities 1 and 2, and this is saying at this one location, well, I don't know, is it, well, it's saying that if you get result 1 at this location, you get 2, and at the other location, if you get 2, yeah, so in some sense, I guess this is entangled between, if you say, what do you get? But you don't specify where it is, what do you get? If you get 1 at the one place, yeah, okay, maybe I'm getting myself a little ball. If you get 1 at the one place, you get 2 at the other place. So I think this itself is an entangled state, I would say. So it's just, I mean, normally, of course, we don't worry about these problems of maybe other observers somewhere else. But if you're trying to do probabilities in cosmology, then I think you have to worry about this. And so I think that Born's rule is not really sufficient for this. So as I said, the failure of the Born rule means that in the theory T sub I, these awareness operators, whose expectation value in the quantum state sigma gives the probabilities, or normalized measures or sentient experiences, at least if it has this form, they cannot be projection operators. However, they could be weighted sums or integrals over space-time of localized projection operators. Say at location, say we have a projection operator at some location denoted schematically by X. So for example, it might be a projection onto a brain state there at that location, but then I'd say you'd have to do some integral or sum over space-time, because if the same brain state occurred somewhere else, that should also contribute to the measure for that observation. So I'm saying it's maybe a sum or integral, but of course, in general, a sum of different projection operators is not itself a projection operator. Now let me talk about the Boltzmann brain problem. I may have to go a bit fast because I'm running a little bit. So in a local quantum field theory with definite globally hyperbolic spacetime, any positive localized operator, such as a localized projection operator, will have a strictly positive expectation value in a non-pathological quantum state. So therefore, if such a positive localized operator, if you integrate it with uniform weight over a spacetime of infinite 4 volume, it'll give an awareness operator with infinite expectation value. So then, of course, you can't normalize it. Now, you might say, well, we'll cut it off. We'll cut off the integral at some finite cutoff time and normalize the resulting. Then for universe, it extends forever with a 3 volume bounded below by a positive value. Then the integrals will be dominated by times of the same order of magnitude as the cutoff time. You put the cutoff time, if the 3 volume doesn't drop below some positive value, then basically the integral will be dominated because it becomes fairly uniform over the space time by times of the order of the cutoff time. And if the late times of probability per 4 volume drops very low for ordinary observers, say the stars die out and ordinary observers that come out by evolution, and they're not just quantum fluctuations, short time quantum fluctuations, that would drop very low, then most of the measure for observations will be contributed by thermal or vacuum fluctuations, so-called Boltzmann brains. So that is, Boltzmann brains will dominate the measure for observations if you do this uniform thing. Now, somebody might say, so what? And they say, well, couldn't our observations just be that of ordinary observers? Or could it be their observations really are Boltzmann brains? But since Boltzmann brains are produced mainly by thermal or vacuum fluctuations, it would be expected that only a very tiny fraction of their measure would be for observations so ordered as ours. So this very tiny fraction, plus the even smaller fraction of ordinary observer observations in comparison with a dominant disordered Boltzmann brain, would be only a very tiny fraction of the measure of all observations. So the normalized probability of one of our ordered observations, which we could use as the likelihood of theory, would be highly diluted by all these, because I'm putting this restriction that the total measure for all observations of the theory should add up to 1, is going to be diluted by these Boltzmann brain observations. So you'd have a low likelihood. You'd have much smaller likelihood than those of alternative theories in which Boltzmann brains do not dominate. Now, of course, you want the alternative theories not to have prior probabilities that are too low, so you don't want them too complex. But the idea is that maybe you need a slightly more complex theory than just having uniform integration to make it so Boltzmann brains don't dominate and dilute the probabilities for our observations. Now, this one's a little this example, but I'm running out of time for this, so let's skip over that. So in summary, Boltzmann brain domination, which is predicted by many simple extensions of current theories, with awareness operators or their equivalent, just say counting observers, being obtained by uniform integration, it gives what I would regard as a reductio ad absurdum for such theories. It makes their likelihoods very small. So they would have very low posterior probabilities. And surely there are alternative theories that avoid Boltzmann brain domination without such cost of complexity that the prior probabilities would be decreased so much as the gain in likelihoods from not having the normalized probabilities of our ordered observations highly diluted by Boltzmann brain observation. So Boltzmann brains, in other words, they dilute they produce a lot of probabilities for disordered things. Therefore, the probability for our ordered observations gets much reduced. And so these theories would then have lower posterior probabilities if you could find some other theory with not too much lower prior probabilities. And the way I see it is the Boltzmann brain problem, it's analogous to the ultraviolet catastrophe, late 19th century classical physics. Physicists then did not believe that an ideal black body in thermal equilibrium would really emit infinite power. And at least I think nearly all physicists today do not believe that Boltzmann brains really dominate observations, but it's a question how to solve them. Okay, I'm running low on time, so we don't have definite answers to this. I mean, one idea that I'm saying is instead of integrating over the thing, you maybe over each hypersurface, you take the density of observations, you divide out by the volume. That might be one way to help. You still need to, if you did that, then the Boltzmann brains would more or less have equal probability in each hypersurface. But then, of course, if time goes on forever, you get an infinity if you integrate over t. So I proposed a rather ad hoc thing to say replace it by dt over 1 plus t squared, and where t is measured in Planck units from the Big Bang or from some bounce. Anyway, I don't believe these are at all final answers, but I'm saying, there are sort of ad hoc ways you can do to get rid of Boltzmann brains. But ideas we'd like to look for something that's more elegant and therefore would have higher prior probability. I think even the prior probability is somewhat low, it still increases the likelihood of the theory by so much that they're better than the theories where you just integrate over them. And then, okay, I think I'll skip over some of this, why we're not ants. Maybe there's some waiting for that. I'll just, I'll just maybe show schematically, okay, I didn't have time to cover all this, that there are many factors that might be in this, in the probability for an observation, the expectation value of that. There might be some weight factor that's higher for human brains to produce consciousness than for ants. Maybe the measure is higher for a particular human to be conscious than, or the consciousness than for an ant. And then if this is approximation where there's expectation values over different space times, and then for each space time there may be integral over the space time of the expectation value of these awareness operators at the space time with some weight factor that depends on where you are in the universe, and particularly the age of the thing. So there's a lot of, I'm saying there's a lot of, even in this, of course, this is approximate because it assumes there's some space-time, whereas the general formalism, you don't even have to have a space-time. You could have some theory of quantum gravity that the theme of space-time isn't fundamental, as long as you can get expectation values for awareness operators. And of course, the crucial thing is to find out what are these awareness operators are. But even in this approximation, there's a whole lot of things that you might vary. There's weight factors, and then this integral for the integral over the space-time. So, okay, well, let's see. There's some things about how our observation could be consistent with Born's rule, and that's basically that this weight factor might not change much with location, and also we just ignore this. Okay, some other things about how you could have a nonlinear theory where maybe you took the expectation value raised to some power, and if that S is close to 1, it would fit observations, but it would. I think it's very hard to pin the exponent extremely close to 1. Okay, so let me yeah, let me conclude there. And I've some of these ideas been visits with Sean Carroll some time past, and where I developed, and then he did tell me that this is not what he considers to be, or some of the Everettian quantum theory, which apparently assumes some particular branching of the quantum state and the probability of observations depending on the branching, but the branching seems to be a highly nonlinear function of the quantum state, exactly how you define the branches. So that seems to be nonlinear, which is logically possible. I'm not arguing against it, but just to me, it seems simpler to assume that these measures for observations are just proportional to the expectation values of some operators. So I'm proposing linearity just based on simplicity, not really based on any logical requirement or whatever. Okay, well, let me conclude. This is, of course, problems for a very distant theory of I don't know whether humans will ever come up with a complete theory, but issues to be raised, and some tentative ideas of how to start tackling that. But it's very much problems that I don't expect to be solved. Well, I certainly don't expect to be able to solve these problems, and I must admit I may be rather pessimistic that anybody will solve these within my lifetime, but I hope maybe we can make more progress on it. Okay, so let me stop there.
Thanks. Thank you very much, Don. So from the audience, if please, if you have any question, ask now.
So it's interesting. I haven't heard anything like this before, so I'm just trying to understand still. So one question. So does this really? So is this kind of new formula for the probability according to this awareness operator that you have, this to the power
Right.
S, general power S? Would that be consistent with having the Bond's rule on systems in the lab, like locally, S to the power 1, S equal to 1?
Yes, I mean, well, we don't know. I mean, we don't know what this S is. I'm proposing, just to simplify the thing, that the S is one, that it is the expectation value. But I guess, so even if it's one, of course, is the question of what these operators are. And I am arguing that at least if you want to do something in cosmology, they shouldn't be just projection operators. But of course, they could be some. I mean, suppose you say you want the results, and your observation includes enough knowledge about your laboratory. Then you'd have to go out to somewhere way off in the universe, probably far beyond our past light cone, to find somewhere else where there's a lab sufficiently similar that the observations made of that lab are identical to ours. But I'm just saying, if there were some other lab, then of course that it might produce exactly the same brain state, or at least enough of the same brain state to have the same observation in that lab. And so the true probability, you might have to take into consideration, well, I'm arguing you should have to take into consideration the contribution from both regions to this. But I think maybe the other thing is, of course, you have your observations, you have memories in the observation, you have a memory of some of the things of how you set up the experiment, and then you have the memory of the result. And so it's in some sense the conditional. In the lab, you're often doing this conditional probability. What's the conditional probability of the result part of the memory given the setup part of the memory? So that, and that, of course, if the conditions are sufficiently ordinary that there aren't crazy things happening at somewhere else in the universe, then those conditional, they might be, even if you did localize it to just the part here, that might be very similar to what's way off somewhere else. And so if you included all of those contributions, it maybe wouldn't change much, these conditional probabilities. In other words, you do, labs, you often say, well, I'll do preparation and then measurement. And so then what's the probability of the measurement giving the preparation? And so my way of looking, you have some record of the preparation, and you have a record that you get of the measurement result. And those your awareness of that can all be in one observation. So the observation can include both a memory of the setup and a memory of the result. And so the predictions of what the of this conditional probability then maybe wouldn't make much difference, even if you said, well, what really contributes to the probability, well, you have to divide probabilities to get the conditional probability, but before doing that dividing, even if you said that really the probability you should include not just one projection operator at one location, but say a sum of ones at many different places. Yeah, so I'm not predicting that there would be anything. I haven't at least thought of any way in which to get a different prediction for, observations in a single lab here at Earth. So I think it's all consistent with Born's rule, but I think it just the fact that it works here in the lab doesn't prove that it really is Born's rule in the sense of being the expectation value of a projection operator.
Okay. Yeah.
Yeah. So I have a question. So in a fully quantum world, in principle, we would be able to model the awareness operator because we know all the interactions as well as it's governed by some Hamiltonian. So
right.
We should be able to model it, I guess.
Well, I guess what I'm saying is that even if we had the complete quantum theory, the bare quantum theory, so we know what the quantum state, suppose we know what the quantum state is and we know what all operators are. Logically, I don't think that determines which operators are these awareness operators. Which ones are the ones that give the measure for observations. Maybe to take an extreme example of that, I don't see anything in presently understand physics about the quantum state that logically implies that there's any consciousness going on. In other words, I could imagine an alternative multiverse, so entirely different physics, some separate physics thing, not part of our universe or multiverse, in which exactly the same quantum state is there, and there's just no consciousness at all. It's a zombie universe. And so I think since that seems to be a logical possibility, it's saying that I don't think you can derive consciousness from physics of the present form that we have. I mean, in other words, I don't think you can derive these awareness operators, even if you even if you had a knowledge of the full quantum state and the full set of quantum operators.
So then would this be in a Hilbert space at all? If we don't know at all about this, can I accommodate in my Hilbert space?
Well, see, I guess what I'm proposing is that besides, yeah, let's suppose it's a Hilbert space. Okay, suppose we say it's a Hilbert space, and maybe for simplicity, let's imagine it's a pure state. I mean, my thing's sufficiently general, it doesn't have to be pure, but let's say for simplicity, it's a pure state in some Hilbert space. So what I'm proposing is that in that Hilbert space, there is something that's not determined by the Hilbert space or the state. There is a preferred set of positive operators. And each one gives the expectation value of each one gives the measure for some conscious perception. So in other words, there's an additional aspect that this quantum state not only exists as a quantum state and has these expectation values, but it actually produces consciousness, different conscious perceptions. And how much of each conscious perception it produces is given by the expectation value of a corresponding operator. So these would be operators in the Hilbert space, but they're not determined by, I mean, they're not logically determined by the Hilbert space. The Hilbert space itself, it just, has a set of all possible operators in it. And so I'm saying that there's particular operators associated that are associated by consciousness. And the zombie universe would have just a case where there would be no such operators. There would be no consciousness. There'd be no, there would be no preferred operators whose expectation values give measures for consciousness.
And does your theory go any way towards solving, say, the quantum measurement problem? Like, say, you have one outcome on a measurement with certain, you do something to the system to get some probability, like,
Right.
apparatus and some time evolution, then after that time, there's suddenly a probability half or something of something realized. And so how will you think about that in your setting?
Well, I guess I would imagine that, okay, that there's, you do some experiment, and then of course there's interactions that go. I mean, if I really want to predict the probably some sentient experience, then I might suppose that there's some operator that tends to have, high expectation value in the physical situation where there's, say, a human brain in some. So now, of course, okay, that's all. I don't know what the operators are there, but you might imagine that with normal seeing and stuff, if light comes in, if light comes in a certain direction and so on, then it excites something in the brain, and then there's one of these operators in there that gets the expectation value of that. So you get some consciousness when some particular part of your conscious awareness when light coming in with a certain direction and a certain frequency and so on, happen. So, but it is an interesting. I'm actually right now kind of working a little bit on a paper of trying to understand decoherence, and whether some people will say, well, decoherence will explain why we see why we don't see huge quantum fluctuations in the observations. And, they'll talk about, well, with decoherence, it tends to, you don't get a coherent state over the large spread in the wave function becomes, it becomes not coherent because it becomes entangled with the environment and so on. But I'm trying to understand how that, and some of these things of saying, well, we have to that eventually we have to take the expectation values of some operators. It might be the characteristic of these operators that might play a big role in saying, why do we see classical observations? Why don't we see this huge quantum uncertainty? And I think that maybe depends on these operators. Now, of course, because I don't know, it's going to be way beyond any knowledge I could possibly have to know what the operators are. But I might make up simple toy models or something for what these operators might be. And in fact, I'm kind of working on something now where just for a particle in one, in one direction, I'm just taking. I'm imagining Gaussian states of different widths as that these operators might be. Well, in this case, maybe even a projection operator. Projection operator, say I don't integrate over the space time, just a projection operator that's a projection operator onto some squeezed state, for example. And then how much squeezing do you get? And it seems like there'd be some probabilities, even if this squeezed state is really spread out very big. And so that might tend to suggest that if it were that way, then maybe you would see a big quantum uncertainty in the thing, but we don't. So maybe somehow, if I took a very simplified toy model of squeezed states, maybe the ones that sort of dominate are ones that are not spread out enormously over position. So it may relate in that, but I don't know. I'm just beginning to try to think a little bit about this, and of course, I want to without having to really go all the way to invoking consciousness, just invoking some simplified operators for, in some toy model.
Okay.
Don, would you say, so let's say, just for the argument's sake, so let's say that Penrose would say that, so there are two observers. I am the observer and Penrose is an observer. Now he believes that the wave function collapses. Now, can I then accommodate this awareness factor in his consciousness?
Well, now, of course, I don't know. I mean, of course, I made this whole framework from sort of the view of unitary quantum theory, that there's no collapse of the wave function. So if you had, I don't know, if you had collapses, what could you do? Well, you might say, okay, there's a whole sequence of states. Each time, say in the Heisenberg picture, you have one state and then it collapses to another state and then that collapses to some other state. And I suppose, of course, you could imagine there's an awareness operators that for each one of these states, or maybe the same operator, but there's a whole sequence of states. And then you have to, I don't know if all these states have you have all these different states. Do they have equal measures in some sense? I mean, I mean, I don't know. Do I calculate the expectation value of the awareness operators in one of these states, and then I do it in another state, and then do I add them up, or what do I do? I don't know. There's some things you could, yeah, I suppose there's some things you could modify, but it just seems, I guess personally, I haven't seen any strong evidence that the quantum state collapses. And so what I'm proposing is definitely not the case that these awareness operators collapse the state. It's just, I mean, in the simplest version, this theory is saying consciousness is an epiphenomenon, that it rides along, it's a consequence of the quantum state, but it has no effect back on the state. Now, it could be interesting. I mean, maybe it's true, but that would be further down the road. Is in some sense, do these operators, do they have an effect on the state? And I even had a crazy idea I put on the archive a few months ago of saying, suppose they did. I personally, I'm somewhat skeptical they could do, but suppose they did. And I'm arguing that these operators, to have all the complexity of our observation, I think these operators have to be non-local. They can't, they seem to have more information than just the local fields at a point. So they're presumably non-local. So if they could have an effect on the state, there might be some acausal propagation within the state. Nice. And so I was raising the question, but this might only be relevant where these operators exist. It might be in human brains. So could somehow in some region in the human brain where the consciousness, if you put a probe in on one side and a probe out on the other side, could a signal cross there faster than the speed of light? And so I did put this out as, I don't think, I mean, certainly my proposal of this sensible quantum mechanics does not propose that these operators have any effect on the state. So I'm rather skeptical they do, but it's a wild idea that seems to be logically possible, that possibly you could have a causality occurring inside conscious beings, even without the quantum gravity effects that you are an expert at, and so on. Even without quantum gravity, there might be some effect, and of course it'd be extremely exciting if that could be found. But it's hard for me to push the idea too much because I don't think it's very plausible. But even though the probability is very low, it's perhaps, if it could be investigated, it'd be worth. But it also seems very difficult because the effect might be very weak, and so I don't know of any clear way to really test. I mean, it could happen, but happen in such a weak way it'd be almost impossible to test anyway.
So, is there any other question for Don? If not, we formally stop the talk. But Don, would you like to be here with us for a few minutes, if it's okay?
Oh yeah, I could stay. Yeah. Why not? I'll just let me get off this share